as soon as, okay, we'll start from current slide. All right. Let me go over a few of the announcements. They published a final exam schedule, and as far as I can tell, they started on the wrong day. They said final start on Monday the 29th. The college academic calendar and the administrative calendar say it start on Wednesday the 30th. So as far as I know, and as far as I'm concerned, we have classes Monday the 29th, and final start on the 30th. For this class, it doesn't matter. Our last class will be Thursday, whatever the last Thursday of next week, 1 week from today, and then you'll get your finals then and turn it in anytime next week. Are any of you graduating this term? Okay, you are. Okay, so you please get yours back to me by Thursday. The rest of you got until the following Monday, but you'll need to get yours back to me Thursday because I have to have your grade in by noon on Friday. So
you said it's next Thursday we're getting it?
Yeah, next Thursday you're getting it, and then you have all except Ariel. You have more than a week to turn it in. Ariel has exactly a week to turn it in. Now, let me mention this while we're at it. The final will exist in two parts. Only one part will actually be the final. The first part is going to be your Chapter 6 test. Whatever we get covered in Chapter 6 will be much shorter than your first 3 tests again, okay? And then the second part will be the comprehensive part, and each of them are going to be 1 page rather than 2 pages, and I think you'll find they're pretty easily done in the time you find. So, that's final exam schedule. They have a couple of other errors on it. The other thing I wanted to say, I forgot to say it in my first class, the last day to withdraw from classes, not that I'm preaching to the choir here, y'all don't need to, but the last day to withdraw from classes is next Tuesday, okay, the 23rd. And that's for mini-term 2 classes or full-term classes. So if you know of anyone who is dangerously in the position they're either can't get any better than a D or an F in the class, not a bad idea to withdraw. Withdrawal does not hurt you academically at all, okay? Some people say, well, it could hurt you with financial aid and stuff, but a D and F hurts you the same way, and they hurt you academically. Now, there is one change, and this is, I found out just in the last week or so. They came out with a new policy, and I was sick during the, the in-service days last fall, so I missed it. And they just sort of mentioned it on the side but didn't emphasize it. If you remember at the beginning of the term when I went over the syllabus, I said at Lawson a D is counted sort of like an F. It's not failing the course, but it's not passing the course either. You have to repeat a D. They've come out with a new policy now, like just about everybody else in the world. A D is considered passing, and you don't have to repeat it unless it's a course in your major. So what's your major? Well, you're going to change yours. What's your major? Engineering. So anything that's in your area 5, which there aren't any engineering courses, your math courses and those kinds of things, you can't make a D in those and have them count. Okay? So you're pre-physical therapy. So anything in your area 5, you have to make a C or better in those. Okay? Because we don't have any physical therapy courses. Well, you don't care. You're graduating, aren't you? Okay. So you're a math major, right? Math major, you can't make a D in the math course. You have to repeat that. Computer science, right? Computer science, can't make a D in the computer science courses. No, don't even try making one in the math course either. Okay. So I'm not going to let you do that either. Okay. But you would be able to get by with it because it's not your major. So that is a new change. I didn't know about it at the beginning of the term. I just found out about it. I think it was Friday a week ago is when I learned that. Okay. I guess I've spent enough time on that. Well, close. Let me mark Jeremiah here. Okay. slowly we're filling up. Okay. Now, why is it starting here? We have done most of this. Usually it gives me an option. Oops, is this it? No, here we go. This is where we're starting this time, I think. Example 1. Any questions? Okay, before we get started. All right, example 1 on page 416. Okay? Showing that two vectors, u and v here, are equivalent. And I think that right at the end of class we hit this and someone came up with a suggestion of what works, and it was absolutely a correct suggestion. I don't remember who it was. Was it? Yeah. I know, and I can't think of his name. Ryan. Okay. And his was absolutely correct. But it's a little more complete to do it the way they're going to suggest here. Okay? How can you show that these are equivalent? What's the two conditions that need to be met for them to be equivalent? Anyone know? I've got to find area. There you are.
Does that have to do with the slope?
Second?
Does that have to do with the slope?
Yes, it does. We actually, with vectors, call it direction, which has to do with the slope. And the other part? What two things do a vector possess? Slope is one, direction is one, and magnitude is the other. So if you can establish that the magnitudes are equal and that the slopes, the directions are equal, then they are equivalent. Okay? How do we determine if the magnitudes are equal? What determines magnitude? Let me get my pen. Second? The length. And how do you determine that? Let's do the magnitude for u, and we'll do the magnitude for v. What do we use to get magnitude? Okay, no clue. That wasn't right. No, okay. All right. It's the distance formula, and how does that go? X2 minus x1 squared y2 minus y1 squared. Okay? And we'll do that for u. U is down here. What would that be? The square root of. That's really easy because your initial point is 0, 0. So that would be what? 9 plus 4 equal square root of 13. Okay? Let's do v. Okay? What's its? X2 minus x1. What is its x2? 4 minus 1 squared plus 4 minus 2 squared, and that would be the square root of 9 plus 4, 13, square root of 13. Absolutely. Okay. Now the second part, that's the magnitudes are equal. That does, yes.
Where did you get that formula from?
The formula is called the distance formula. Okay. Let's see if all they say is the distance formula. If you go back early in the book, I think the chapter is called P, the preliminary chapter. No, it isn't. I think they just want you to know that. Okay. Yeah, it's just a formula they think that you probably should know already. It's called the distance formula. It's just the difference of the x's squared plus the distance of the y squared gives you the square of the length. So the square root of that gives you that. It's Pythagorean theorem, basically.
That's how you got the magnitude?
That's the magnitude. Those are the magnitudes. Okay. Now, directions. Okay. I like that someone said that. We say, yeah, magnitude and direction. Someone said slope. What is your slope? Which indicates the direction. So M for U would be what? What's the formula for slope?
3 over 2.
Is what?
Wouldn't it be 3 over 2?
Okay. You're using what we've already determined. 3. Okay, for U, yeah, it would be 3 over 2. You're right. Change? No, not 3 over 2.
2 over 3.
2 over 3. Yes. Okay. Making me write the wrong thing down. Yeah. Okay. 2 over 3. So what's the magnitude? I mean, the slope for V? It's what?
Oh, no, never mind. I'm being crazy. 2 over 3. 2 over 3.
It's 2 over 3 too. It's y2 minus y1 over x2 minus x1. It was easy to do for V because x1 was 0, 0. Even Christian could do that. Okay, but this one is your change of y's were 2 and your change of x was 3. So sure enough, the slopes are the same. And the slopes are indicative of what the directions are. Okay? Magnitude and direction. And what Ryan said just before class was over with, which was, I thought, a really clever thing, he said the delta x's and delta y's are the same. Well, guess what you have here? The delta x squared plus delta y squared. Take the square root of that, that would be that. Here you have delta y with delta x. So if the deltas are the same, if the change of y and the change of x's are the same, then both the magnitudes and the slopes are the same. So it was pretty clever of him to notice that's all that you needed to know. But I wanted you to be familiar with the formulas because some people weren't. Okay, so just to reiterate that. Perfect. Let's see, that's how we did it. Let's see how they do it.
So you need to just find one of them or both of them?
What?
Like the magnitude and the slope?
Yes, you need to prove that they're both equal. That the magnitudes are equal and the directions are equal. Okay? Otherwise it's not. Equal magnitudes but going different directions, they're not equivalent. And same direction with different magnitudes, they're not equivalent either. So you have to show both. But what Ryan said was if the delta x's and delta y's are the same for both of them, then obviously the slope formula works and the distance formula works. Okay, so there it is for PQ, which y didn't they call it? What was that? That was U in ours, but they call it PQ, which is fine. And they named it as PQ here too. Okay, but that was U, and there's V. So PQ is the same as U, and that's the square root of 3 minus 0 squared plus 2 minus 0 squared, which is square root of 13. They jumped right to the chase. And then they did RS the same way, square root of 4 minus 1 squared plus 4 minus 2 squared, also square root of 13. Magnitudes are the same. When you go to slopes, both line segments have the same direction because they're both directed toward the upper right, having a slope of 4 minus 2 over 4 minus 1, which is 2 over 3, and 2 minus 0 over 3 minus 0, which is 2 over 3. Perfect. So if you can show that both the magnitudes are equal and the slopes are equal, directions equal, then you show they're equivalent vectors. Because PQ and RS have the same magnitude, same direction, U and V are equivalent. Now they do a thing of they're calling these vectors by that name and these vectors by this name, And they don't say these two are equivalent, but they say these two are. It's picky. I mean, there's no real reason for that much distinction. Okay. Now, let's move on to component form of a vector. The best way to write a vector, in my mind, is in component form. And actually, it's only been in the last few decades that I've even seen this. Back when I was first learning vectors, we never had this form and called it by this name. It makes perfect sense. The directed line segment, whose initial point is the origin, and is often the most convenient representative of the set of equivalent directed line segments. So if you had just moved the V down to the U, you'd have seen that we're exactly equivalent. That representation of the vector is said to be in standard position. When you have its initial point at the origin, no matter which way it's heading, if the initial point is at the origin, that's in standard position. The vector whose initial point is the origin, 0, 0, can be uniquely represented by the coordinates of its terminal point, V1, V2. If that's the endpoint, like our last was 3, 2, that last one, since it started at 0, 0, that is also the vector representation. The component form of the vector V, then, that with those endpoints, initial and terminal points, can be written as the vector V, V1, V2. Now that almost looks the same, doesn't it? With parentheses, that means it's a point. With angle brackets, that means you're talking about a vector. Vector here, point there. Same two numbers, okay? And anytime you have a vector in standard position, they will be. The terminal point will be the representation, same two. But these are coordinates of a point. These are components of the vector. The words sound alike. These both start with COs, but they're different. These are the coordinates of a point. These are the components of a vector. But if that vector is in standard form, those coordinates and the components are exactly the same. Anywhere else, they won't be, but they will be in that case for a standard form. And that's the most convenient way to write a vector, in component form. Okay. We'll see examples of this later. Everybody got it, or need that up a little longer? Okay. The coordinates V1 and V2 for the point are also the components of V when it's in standard form. Okay? If both the initial point and the terminal point lie at the origin, then you have a problematic vector in my mind, because that's the zero vector. And in reality, we have to have it, because for a set of vectors to have all the properties it needs, you've got to have the zero vector. The zero vector is this is in two space on the plane. Both components are 0, 0. And the reason I call this problematic, because what's the two things that a vector has to have? Direction and magnitude. This has neither. Okay? If you think about it, what's its magnitude? 0. It doesn't have a magnitude. Okay? What's its direction? Who knows? If it's at the same point, how do you know which way it's pointing? Okay? It doesn't have a direction, and it has a 0 magnitude. So, but it's still a necessary vector to have. Okay? So, that's the one and only problematic one I think we'll have. Component form of a vector. The component form of a vector with initial point P1, P2, terminal point Q1, Q2, if this P is not the origin, then the component form will be, just as Ryan suggested before, the difference of the value. Q1, the x1 minus x. We were calling this x2 and x1. Now it's Q1 and P1. But the first component of this one, the terminal point, minus. Always do terminal minus initial. Always do that for your delta. Terminal minus initial. Terminal x minus initial x. Terminal y minus initial y. Okay? And that, again, as Ryan said, I don't know if he used this term when he was leaving, but I think he did, and he said I think he said the delta x and delta y, which is exactly what they're doing. Okay? The change of x, always a final minus initial, terminal minus initial, for x and y. That then is a component of v, and that will be a vector v. The magnitude of the length of it is then simply, remember, this is that delta x and delta y. Delta x squared plus delta y squared. This is v1 squared plus v2 squared. So if you know the component form of a vector, square root of their sum of the squares. It's just that easy. Okay? If this magnitude is exactly 1, then we call v a unit vector. Okay? And if the magnitude is 0, that has to be the 0 vector. Now notice the number 0 is written in normal text, normal type. The vector 0 vector is written in the bold. It's the only vector you use a number to identify it. It's a 0 vector. Notice we don't say this is a unit vector, so it's bold 1, because it could go in any direction. So we don't do that, only 0. It has no direction. Okay, now let me give you a little hint here. Notice, and I said this last time, certainly when you're writing it with initial point, terminal point, PQ, you put the arrow over it and you're talking about the vector, not the line segment PQ, but the vector PQ, from initial to terminal. I don't write bold, so I said in general, I'll be writing V with an arrow over it too to indicate it's a vector. Okay? With one exception, or maybe many exceptions. If V is a unit vector, then I put a caret over it, a housetop. To me, that says unit vector. So that's why, if I know it's a unit vector, I'll put that over it rather than an arrow. If I don't know, I'll put the arrow. If I later find out it is, then from then on, I'll write it with the housetop. It's just a habit I've gotten into, but I like to do it to remind myself, we know that's a unit vector. Okay. So the book doesn't go into that, I do. Okay. So you'll know, if I do that, if you see that, that's a vector, but it has magnitude of 1. Okay.
I have a question.
Yes.
On the first example, and the second one,
Yeah.
the component form is the magnitude formula is different than the first one, right? The other one was x squared minus x1 squared. Yeah. I don't know how to say it. This one right here.
Yeah. This is the change of x's squared plus the change of y squared, right? Mm-hmm. That's exactly what these are too. It's just they named them differently. Okay. They named this one P1, P2, and Q1, Q2 rather than X1, X2. Okay. They named it that.
So it's the same.
Yeah, it's the same thing. Change of x's, change of y's. Yeah. Okay. Good deal. Good question. All right. Now, two vectors U, which is U1 and U2. This is component 1, component 2. X component, Y component. Okay. And this is how they're going to name them from now on, probably rather than X1, Y1, X2, Y2, that kind of stuff. And component and vector V, which is V1, V2. These are equal. Remember earlier we were calling them equivalent, but we now call them equal if and only if the first components are the same and the second components are the same. Okay? That's the only way they will be equal. But remember, these are written as whatever your points are, P and Q, that would be the change of y through the change of x. This is the change of x, that's the change of y. The change of x, change of y. Those are equal to then the vectors are equal. And they both have to be identical in component form. So see, component form, real easy to tell the quality of vectors. Where if you write them in the other forms, not quite as easy. For example, in example 1, the vector u from P1 with P, which is 0, 0, to Q, which is 3, 2. That vector in component form was, okay, drag it out, 3 minus 0, 2 minus 0 would be 3 here. You could have just written this because you knew the initial point was 0, 0. But the vector v that was from R, 1, 2 to S, 4, 4, then that in its component form was 4 minus 1, always final minus initial, terminal minus initial, 4 minus 1, and comma, 4 minus 2, close bracket, angle bracket. And this would be 3, 2. So once you see this is the same as that, those are equal vectors. So that was the other way we could have done it. And that's really probably what Ryan, where he took that. Change of x's, change of y's, they're the same. Yep, they have to be the same vectors. Without having to show that the magnitudes are the same and the directions are the same. If they have the same components, they're the same vector. You know, they're equal vectors. Okay, so again, component form, easiest way to deal with things. It can answer all your questions, okay, whether you have them or not. Okay, so let's do example 2. Find the component form and the magnitude of the vector v, which has initial point 4, negative 7, terminal point negative 5, negative 1, 5. So first let's do component form. What is v in its component form? How would you get that? Help me, somebody. Okay, what would its component form be now that Demetrius is here? Okay. What would its component form be? Negative 1 minus 4, comma, 5 minus a negative 7, close bracket, which would then be, v would be, ooh, that's an ugly angle bracket, isn't it? Don't answer that question. Okay. What would that be? Negative 5, comma, second, next, 12, okay, positive 12, got it. Okay, now that you've got the component form, how do you determine its magnitude? Okay, which one? Okay, you could do that, or if you'll notice, let's go back, this is why I said which one, because right here we came up with this is what you're saying, right?
So we can use that.
You can do that one. Okay. All right, we quit talking about him, he's here now. Okay. All right. Okay. So, what would that be then? Square root of? You say 25 plus 144, which would be the square root of? Second? A little louder. 169. Anyone know what that is? Square root of that is? Second? 13. Exactly. That's one of those Pythagorean triplets. 5, 12, 13. Like 2, 3, 4? No. 3, 4, 5 is the Pythagorean triplet. The next one is 5, 12, 13. There are others too, but that's another one. Pretty interesting how you can do those well, we won't get into it here. It's an interesting way to do that. That would be a pretty interesting paper topic if anyone wanted to pursue it. Pythagorean triplets, okay? You'll find a lot of really neat stuff with that. Now, a couple things to notice. What if the 12 had been negative rather than the 5, or either both the 12 and the 5 would have been negative? What would have been your magnitude then? Say again?
Would it have been the same?
It would be exactly the same because magnitudes are always positive. It doesn't matter what the sign of either of the two components is, the magnitude is always a positive number. That's why I kind of like to use the double bars. It's a lot like an absolute value of a real number is a positive number. Well, the magnitude of a vector is always a positive number. Okay. I'm not sure that's why they did it, but it's a good mnemonic device for me. Okay. Let's clear what I did so you can see how they did it, which I think is going to be very close to the same. Oh, boy. So, wait, we give names to them. Let P be 4, -7, because that was always our initial point, which we're going to call P1 and P2, which really clears things up a lot, doesn't it? And Q be -1, 5, which we'll call Q1 and Q2, which adds another level of importance to it. And then your components of the vector V1, or V1 would be, why did they have to have Q1 minus P1? I'm not sure. We just did this minus that. They just went straight there and did it, you know. But if you need that, go for it. That would be your first component would be the difference of the first components. Always terminal minus initial. And then that would be -1 minus a 4, okay? And then that would be a -5. And your V2 was Q2 minus P2, which we just went straight for 5 minus a -7, which is what they do now. And that gave us a +12, okay? So your vector V is component form -5, 12. Magnitude then would just be the square root of the sum of the squares. Square root of -5 squared plus 12 squared, square root of 169, which happens to be 13. All right. Now we're moving to vector operations. Okay. These are appendectomy. No, these are different kinds. Okay. So what are our vector operations? Two basic vector operations are scalar multiplication and vector addition. Okay? In operations with vectors, numbers are usually referred to as scalars. Numbers meaning things without direction, just magnitude. Those are called scalars. And things, of course, if they do have direction, then they're called vectors. In this text, scalars will always be real numbers. We're not going to use any complex scalars, just real numbers. And geometrically, the product of the vector V and the scalar K is the vector that is exactly the magnitude of K, absolute value of K, times as long as V. So if K is a big number, it's going to be an expanded V. Same direction, just longer length. If K is a small number, less than 1, then it's going to be a reduced V. It's scaled up or down by the factor K. Now, those are magnitudes, okay? Why did we put the absolute value on it? Well, the sign of K would then change the direction. But it doesn't change it randomly. It's either the direction it was going if it's positive, or exactly the opposite direction if it was a negative. But the magnitude would be absolute value of K. Okay, when K is positive, KV has the same direction as V had. It's just either longer or shorter depending on the magnitude of K. When K is negative, KV has exactly the opposite direction of V. Nothing else, no other direction, but exactly opposite. It's shown in this picture. So if this is your vector V, okay, this would be 1/2 of V, because it has exactly half the magnitude of V. This would be 2V, has exactly twice the magnitude of V. This is minus V. It's exactly like V, except V is going this direction. This is going exactly in the opposite direction. -3 halves V would be opposite direction with 3 halves, 1.5 times the magnitude. Make sense? Okay. Always same, I don't even want to say slope. They're parallel. Let's just put it that way. Okay. Now, another vector operation is the sum of two vectors. That was scalar multiplication. This is sum. So let's say you have a vector u here and a vector v over here. Okay? Then the sum of u plus v is also going to be a vector. In the vector form, by joining the initial point of the first vector u to the terminal point of the second vector v. Okay? So, actually, I usually do it the other way. I usually do the terminal point of u to the initial point of v. But guess what? It doesn't matter. If this is u and that's v, okay? Well, they did do, if I'm not mistaken, they say the initial point of the first value v. So they said it one way and did it the other way. They did it the way I did. You do u, and then on the terminal point of u, you put the initial point of v, whereas they said it backwards here. They said join the initial point of the first vector with, oh, I know what they're meaning here. They didn't say it well, is what they said. If they put the initial point of v on the terminal point of u, and then put those in place, then join the initial point of u with the terminal point of v. They left out the part that you had to put them the other way first. So, rather strange but true. Remember, you can move a vector around anywhere you want to as long as you don't change its magnitude or its direction. You can move this one around anywhere it wants to. So they left the u where it was, and took the v and moved it up here, and that's how they got this. And then joining the initial point of u to the terminal point of v, that is your new vector u plus v. Question for you. Is u plus v always have a greater magnitude than u and v together, individually? Not a very fair question, but the answer is no.
Shouldn't they be the same?
Huh?
Shouldn't they be the same?
No. In fact, u plus v here is not as long as u added to v. That would have been long. If these had been in the same direction, that would have been the same, right? But as long as they're not in the same direction, the magnitude of the sum is less than the sum of the magnitudes. So it's always less than or equal to. What's even worse, it can be shorter than either one of them. What if v was a vector in this direction? Then the sum vector would be like this, right? So, yeah, it can be much smaller. It can even be 0 if they're exactly opposite of each other. So, in regular math, if you're adding two numbers, you usually expect to get the larger number, a larger number as a sum. Unless, of course, they're signed numbers, and then all bets are off, right? Same thing with vectors. All bets are off, okay? So, this technique that we just showed here, is called the parallelogram method. Because if you do what they said at the top and started with v here and then added u to it, this is v, start with that, and then take u and add to it, you get to the same point. Okay? We'll come across that later. But what do you have there? You have a parallelogram. Because these two sides are parallel and those two sides are parallel. And what the sum vector is the main diagonal of that parallelogram, okay? I hate to even say main diagonal because later we'll see cases where it may actually be the minor diagonal, but it's a diagonal anyway. This technique is called the parallelogram wall for vector addition. It's called the vectors u plus v, often called the resultant of the vector addition, is the diagonal of the parallelogram having adjacent sides of u and v. Okay? Now, and notice I say adjacent sides of u and v. Let's go back to that. Notice You don't have u, v, yeah, you have to have the adjacent side, u and v, u and v. V and u, v and u, yeah. However it is, the adjacent sides is even this is v and u. Okay. They have to be adjacent to each other. Okay. So here's definitions for vector addition and scalar multiplication. If u, and we're doing two-dimensional vectors now, u1, u2, x component, y component, and v, v1, v2, x component, y component. And they don't have to be x, y, but let's just use that for example. And some k is a scalar, any real number, just has to be a real number. Then the sum of u and v is the vector. Now, what did I say before? Component notation is the way to go. If you had to add all your vectors doing parallelogram methods, number one, you're not going to be very precise, and number two, it's a pain in the neck, or maybe not in that order, but whatever. But in component form, add the v's, the first component, comma, add the second component. Okay? That's it. Can you get much easier than that? The scalar multiple of k times u is just, you can almost picture this as a distribution the constant inside the vector angle brackets. And there you have it. Ku1, comma Ku2. Scalar multiple. Component form, easiest way to deal with all these issues. Okay? Everybody got it? See people still writing, so I'll give you time to finish. Got it? Everybody got it? Okay. Now, another concept here, the negative of a vector. The negative of v, vector v, vector v is v1, v2, is just negative in front. Now, they bolded the negative. You really don't have to, but I guess it's okay to, or you can't tell whether it's bolded or not. Maybe it's not bolded, okay? But it's the same as a negative 1, right? If you don't see a coefficient, you understand it to be a 1, and negative 1 times v. Well, negative 1 times v, remember v is v1, v2, that'd be negative v1, comma, negative v2. There you have it. It just flips it over and goes in exactly the opposite direction. What's that? The magnitudes are positive. The vector could be in any direction, okay? Otherwise, we'd be hurting, never get back up to you. Okay, of course we can back up. Okay, so you can subtract two vectors to them now that you know what the negative of a vector is. So just like it is with sign numbers, the difference of two vectors, u and v, u minus v would be u, the first one, plus the opposite of the second one. That's how you add subtract sign numbers. That's how you subtract vectors. The first one plus the opposite of the second, the negative of the second. Okay? So that would simply be u1 minus v1. You don't even have to do this thing. u1 minus v1, comma u2 minus v2. Now, again, remember that these can be positive or negative anywhere you want to, but you follow this rule. That's your difference. Now, parallelogram method still works, but it's sort of a pain in the neck. Okay, in my mind anyway. You start with the vector u, and this is your vector v, but this would be plus the opposite of v. So you start with u and then put the opposite of v in this direction. This now is u minus v. Okay? Now, they put it up here, but it's also down there. They're the same. U plus negative v is the same as u minus v. Those are the same vectors. Okay. So, I don't ever mess with that. It's so much easier to use component vector. If I do mess with it, I'm very careful that I get the things right. Any questions? Okay. To represent u minus v geometrically, which we just did, you could use the directed line segments with the same initial point, which is sort of bizarre. The difference u minus v is the vector form from the terminal point of v to the terminal point of u, which is equal to u plus a negative v, as shown in the previous figure. Am I about to sit down and try to remember all that? No. Okay? Just use component form. But what they're saying is, rather than put them tail into tail, just put them the u and the v from the same, and then do it from the terminal point of v to the terminal point of u. Always, this will be the terminal, okay? And this you do that. So this is what they're saying is another way to look at it. Rather than risk getting it backwards, I'm going to do it the other way, okay? Even that way is better to me than that. But if you remember it, fine, go for it. But I don't use geometrically. I use the components, and they're so much easier to do. Okay, component definition of vector addition, scalar multiplication are illustrated in example 3, which we're going to do in just a second. In this example, notice that each of the vector operations can be interpreted geometrically. Yeah, they can. Why mess with it, though, in my mind? But anyway, so let's do example 3. Okay, here's v, and there's w. v be negative 2, 5, and w 3, 4. Find each of the following. What is 2v, or not 2v? Okay. What would that be? Okay, we'll take our time with it. That would be 2. This is such a pain in the neck sometimes. Still a pain in the neck. Yeah, there it is. This would be 2 times negative 2, 5. That's vector v. So what would this be? Negative 4, comma 10. Is a vector component notation the easy way to go? Okay. W minus v. Okay. I would do it this way. W is 3, comma 4 minus v is negative 2, 5. What would that be then? Negative 1. Perfect. Component notation is the way to go, folks. It's 3 minus or minus 2. I mean, the signs look easy this way. That's the 3 plus 2 is 5, and 4 minus 5 is 1. Perfect. Okay. Now, what would this be? V plus 2w. Do it in component notation. Negative 2, 5 plus 2 times 3, 4. I think I got them right. Okay. What would that be? And take as many steps as you need. Okay, negative 2, 5, that's v, plus, and then double that one, and you get 6, 8, and then add those two, and you get 4, 13. Perfect. See how that worked? Any questions on it? Question? You look?
No, I was just
disturbed.
I wasn't here when y'all were doing a component for
Okay. Is it making sense?
Oh, yeah, that makes sense.
All right, good deal. All right. While we're waiting, I didn't say this at the beginning of class, I probably should have, but I'm glad I waited till more people were in here. Just a little hint. We talked about how close to the end of the term we are, and I have received fewer than half the research papers. You have uno weekend left. If you are planning to use a weekend to work on it, you only have one left, okay? Test 1. 2 people, 2, have not turned in test 1. One of them's not here, one of them is here, okay? Test 2. Barely half of you have turned in test 2, maybe not even half, okay? Test 3, 2 people have turned in test 3. You're about to get test 4. Well, you're going to get that next Tuesday. No, next Thursday, a week from today. Okay. So please, folks, get your test and your research papers in. Please. Yes.
On B.
B?
B, yeah. 5 minus 4 is 1, right? So 1 is
Okay. First.
4 minus 5.
Okay. Yeah. 4 minus 5.
How would you do that?
Yeah. They gave them to a VW, but then they asked for W minus V. So they flipped them. I hope they wrote them right. But, got it? Okay. I'm going to clear this for now so that we can see how they did it. And if I did mess something up, hopefully they'll correct it. Okay, 2V is exactly 2 times -5, -2, which is 2 times -2, comma, 2 times 5, and that would be 4, -4, 10. And that geometrically just doubles the vector. Okay, here was -2, 5, there's -4, 10. Exactly doubling both components. Okay? Here is W minus V, W being 3, 4. Subtract from that -2, 5. In component notation, it makes it so easy to do. 3 minus a minus 2 is 5. And, oops, there they did it. Okay? And 4 minus 5, that would be 5, comma, -1. Done. I think that's what we got. Okay? And then this, and here they did that. Now, again, I don't find this particularly helpful. But this, if I were going to do it geometrically, this is what I would do. But they didn't show the original vectors. Well, they did on an earlier slide. Your vector V was here like this, okay, parallel to this over here. And then they said if you draw this from here to here, that's the same thing. And sure enough, that's what it is. This is how I would do it if I was doing it geometrically. I'd write your W, just like it was, then do the opposite of V from that point down here. There's your W. Okay. Good deal. Any questions?
Are we going to have to graph that?
What's that?
Are we going to have to graph that?
If you choose to, you may. I don't want to grade them that way, though. I'd rather you do it the easy way. Okay. And then the sum of V plus 2W, if you write it in component notation, it just makes perfect sense. V is -2, 5 plus 2 times 3, 4. That'd be -2, 5 plus 2 times 3, comma 2 times 4. I'm glad they did that. That makes it easy to see. That is 2, 5 plus 6, 8, exactly like y'all got, and that's, all right, negative 2 plus 6, comma, 5 plus 8, and that was 4, 13. Wow, can they stretch it out? Yeah, they can. So here's a sketch of that. V being this one here, negative 2, 5, and then we add to that twice W, which was that. So, make sense? I'm so glad they did the graph. Makes me feel warm and fuzzy inside. But it just shows that it does work. Okay. Now, continuing with vector operations, vector addition and scalar multiplication share many of the properties with ordinary arithmetic. Okay? So now, for these properties, we're going to assume we've got three vectors, u, v, and w. And we're going to assume they're all in the same, and this is not fair to say, but the same space. In other words, they're all planar vectors or they're all space vectors. So far, we've just been doing planar vectors, so they're all in the xy plane. So it'll work even if they're not, but they all have to be the same dimensions. Okay? We haven't talked about it. No. And let C and D both be scalar numbers, any real number in the world. Okay? Even 0. Then the following properties are true. And if you remember, I said that you can do V plus W, get the same as if you did W plus V. Okay? Or U plus V is equal to V plus U. This is called the commutative property of addition. It doesn't matter the order of adding vectors. U plus V or V plus U, you're going to get the same result of that. Number 2, it doesn't matter how you associate the vectors. This is associative property of addition. You can add U plus V first and then add W to it. Or you can add to U the sum of V plus W. They're all going to work out the same. Now, if you're doing 3 or more, what you usually do is wind up with, here's the first, there's the second, there's the third, and then there's your answer, or any order you wanted to do them. You're going to get what they call then polyhedrons. They won't be parallelograms anymore. Once you get past 2, they're no longer parallelograms. So I don't want to mess with them. Okay, number 3. U plus the 0 vector. It's got to be U, because this is 0, comma 0. So this is U1, U2. U1 plus 0 is U1. U2 plus 0 is U2. So U1, U2 is U. Okay. So yeah, that's called the identity element of addition. This is a 0 vector. And because you have to have one, that's why we have to have a 0 vector. Okay. It doesn't have any direction, it has no magnitude, but it's still a vector. Number 4, if you add a vector to exactly the opposite of that vector, so you do this one this way and add to that this one, you start right back where you started, which gives you the 0 vector, which has no magnitude or no direction. Okay? Now, this is a stretch, but it's true. This is a form of associative property of multiplication, but they're not vectors. You have 2 scalars and 1 vector. A scalar times another scalar times a vector is the same as 2 scalars times a vector. This is a form of associative property of scalar multiplication. We haven't even talked about vector multiplication, so don't even confuse those. Or distributive property, again, you have to have 2 scalars and a vector, but down here we'll have a scalar and 2 vectors. So we'll have 2 different ways of doing this. The sum of 2 scalars times a vector is the same as 1 scalar times a vector plus the other scalar. So that's sort of a distributive property of scalar addition over vector multiplication. Number 7 is a scalar on the outside and the sum of 2 vectors here. You can add 2 vectors, so that's no problem. So this is the distributive property of scalar multiplication over vector addition. That was vector multiplication over scalar multiplication over scalar addition. This is scalar multiplication over vector addition. This is Cu plus Cv. Same deal. Number 8. Whereas this was the identity element of addition of vectors, 1, not of vector 1, the scalar 1 is the identity element for scalar multiplication. 1 times u is u. Of course, that's 1 times u1 is u1, 1 times u2 is u2. That's just u1, u2 is u. Or 0 times the vector u winds up being the 0 vector, because this is 0 times u1, which is 0, 0 times u2, that's 0, u1, u2, 0, 0 is the 0 vector. So there is the 0 principle, multiplication principle, multiplied by 0, whatever you want to call it. And number 9, now this is a little different, but it does make sense if you think about it. If you have any scalar c multiplied by any vector v, and you do the magnitude of that vector, that is a vector, that's the same as the absolute value of c times the magnitude of v. And I think as Brian was saying earlier, or maybe misstating earlier, it's magnitudes are always positive. Magnitude of a vector is always positive. Vectors are always positive, but the magnitude is. So therefore, the magnitude of c times the vector has to be, you can't just have c times the magnitude of the vector, so c could be negative. And this can't be negative, so you have to use absolute value of c times the magnitude of v. So everything stays positive. Okay? That was a property of real numbers, by the way. That's unique to vectors. All right. Let's see where we were. Properties of vector, yeah, blah, blah, blah. Okay. They are skipping examples 4, 5, 6. No, they're only skipping example 4. Sorry. I wondered where that went. So let's do example 4 before we move on. All right. Example 4. By the way, William Rowan Hamilton, an Irish mathematician, did some earliest work with vectors. He was considered probably the greatest mathematician to come out of Ireland, I think I read somewhere. There was a Scottish physicist they mentioned here, James Maxwell. His middle name was Clark, but they spell it Clerk. Scots do that. Okay. But the two of them really did some very creative things with vectors. So let's do example 4. I seem to have lost, for some reason I put it in my pocket. Oh yeah, we got that. Okay. Let u, vector u, be 1, 3, love component notation. Vector v is negative 2, 5. I'm not sure these aren't the same as we had before. One of them is similar. Okay. Yeah, negative 2, 5 is similar. Find the magnitude of each scalar multiple. Okay. A. The magnitude of 2u. By the way, that vector right there is very famous because that's one they named the Happy Birthday song after. Okay, never mind. Yeah, 2u. All right. What would this give you? You want to multiply first and then take an absolute value? Or maybe just do 2 times the magnitude of u. Wouldn't that be pretty easy? What's the magnitude of u? Second? Square root of 10. There's your answer right there. 2 times the square root of 10. If you had multiplied first, that would have been 2 comma 6. Then the square root of 2 comma 6 would be 4 plus 36, and that would be 40, and that would be 2 root 10. Much easier doing it this way. Don't you think?
So you just did 1 squared plus 3 squared, and took the square root of that?
Yeah, 1 squared plus 3 squared. Yeah, square root of, that's where we got it. Yeah. Sorry, I probably should have written all the steps. But he jumped right ahead and told me the answer, so I was lazy too. Okay. The B, absolute value of negative 5u. What would that be? Second? Now it's absolute value of negative 5, which is 5 times 10 again. Once you've done the magnitude of u, it's the square root of 10.
How do you get the magnitude
Okay. Yeah, I think this is what Christian's question was too. The magnitude of u is equal to the square root of the sum of the squares of its components. 1 squared plus 3 squared. Sum of squares of its components. And that would be the square root of 1 plus 9, which is the square root of 10. See? Okay? And then when you get down here, it's the absolute value of negative 5, which is 5 times magnitude of 10, which is already times the square root, magnitude of u, which is the square root of 10. So once you've done the square root of u, the magnitude of u, which is square root of 10, then the rest is just writing down numbers, okay? C, though, deals with v. So C is the magnitude of 3v. Well, that's the absolute value of 3, which is 3 times the magnitude of v. Well, what is the magnitude of v? Let's write this one out this time. The square root of what? Second? Okay. I don't think so. I hope not, anyway. Yeah. Second?
Do you want the whole thing or just...
Okay. Okay, wait. Let me back up and do it a little more slowly then. This is the absolute value of 3, which is 3, okay, times the magnitude of v. Okay. The magnitude of v is the square root of negative 2 squared plus 5 squared. That's how you do magnitude, right? 3 times the square root of 4 plus 25, and this is 3 times the square root of 29. Okay, so since you know what the magnitude of v is, then if I said, what would be minus 5 times the magnitude of v? That would be 5, because you take the absolute value of that times 29. Once you've done the magnitude of u or v, you don't have to do it again. It's always that, root 29. And it's always positive, okay? Magnitude is always non-negative, okay? Always. Okay. Let's see what they got in the book. 2 root 10, good for them. 5 root 10, good for them. And 3 root 29. All right. That leaves Athens short to root 29. Okay. Now we're ready for unit vectors. Good. Can we move on, or some still writing? Oh, you're good. Okay. All right. Now we mentioned unit vectors once earlier. Now we're going to talk about them a little more generally. In many applications of vectors, it is useful to find a unit vector that has the same direction of the given non-zero vector. Why couldn't you have the same direction of the zero vector? It doesn't have any direction, does it? So any non-zero vector v. To do this, you can divide v, which is the whole vector there, by its magnitude, and guess what? Now you guarantee that it has a magnitude of 1. So u is a unit vector. Now in this case, use a unit vector, which is the vector v divided by the magnitude of the vector v. Or you could think of this as 1 over the magnitude of v times vector v. However you want to write it. I don't see any advantage of that to this, but whatever. Unit vector in the direction of v. notice that U is a scalar multiple of V, of course, because this is a scalar quantity right here. 1's a scalar and magnitude's a scalar, so that's a scalar quantity of V. If V was a little bitty short vector, then 1 over root V is going to be a big number, okay? 1 over magnitude of V, okay? If V is a great big long number, then square root of V is going to be a big number. You're dividing by that, it brings it back. So this gets it back. It normalizes the vector to a unit length, okay? The vector U has a magnitude of 1, always, and is always in the same direction of V, okay? The vector U is called the unit vector in the direction of V. What's that? I do one. If I know U's a unit vector, I write it like that. If I don't know this is a unit vector, I write it like that. Both of those are vectors. I know that one's a unit vector. Okay. But in the book, they just put a bold, so they have to tell you whether it's a unit vector or not. You can tell mine because I put a house top if I know that it's a unit vector. Okay. Ready for example 5? Oops, example 4. Evidently, they left out example 4 from the earlier edition, and this is example 5 in the book, 4 on the slide set. Sorry about that. Let me make sure it's the same one. Find the unit vector, they say U here, in the direction of V, which is negative 2, 5, yeah, and then verify that unit vector has a magnitude of 1. Okay? So, we want to find the unit vector U in the direction of V, and then we'll verify it has a magnitude of 1. So what will that be? I like to put this sub V. That means it's in the direction of V. How would you do that? Any ideas? You put V in the numerator, that gives it the direction, but then you do what? Divide by the absolute value of V. Well, not absolute value, magnitude of V. Okay? So this will be the vector negative 2, 5. That was easy. But what's this magnitude? The square root of 29. We just did that not long ago. So the vector U will then be the vector negative 2 over root 29, comma 5 over root 29. Now, if before, in an earlier lifetime or earlier in the book, they never put radicals in the denominator, they've gotten over it. Okay? They routinely put them in the denominator. Now, you don't have to write that as negative 2 root 29 over 29. But if you write it that way, you certainly can. Okay? Okay? We think we found the unit vector in the same direction of V, but we haven't verified it is a unit vector. So how would we tell if that's a unit vector? The square root of negative 2 over root 29 plus squared plus 5 over root 29 squared. Okay? Oops. I can't write. Okay. What would this be? The square root of negative 2 squared is 4 over, and root 29 squared is 29 plus 5 squared is 25 over 29, and guess what that is? 29 over 29, which is pretty close to square root of 1, which is 1. Can we drag it out any further? See how easy that was? Okay? It's the vector itself divided by its magnitude. As long as that vector is not the zero vector, that's guaranteed to give it to you. So I know it's getting close to time, so let me erase what I did, and let's see what they did. Unit vector has a direction, in the direction of V would be minus 2, 5 over the square root of negative 2 squared plus 5 squared. And that is They put the 1 over 29 in front times -2, 5. And then they wrote it this way. Why they did it that, I don't know, but that's it. And then they verified it by squaring those, and sure enough got 29 over 29, which is 1. Good deal. Good deal. Thank you. All right. Let's see if we got any homework exercises here. Let me first show how far we got. We are ready for example 2 next time. No, example 6 next time. Doesn't look like they, oh no, we're ready for the bottom of the page. Okay, that's what we'll pick up next time. Get this in place. Homework exercises here include any of the odds, do number 9, and that should be at Calc Chat, and then either 11 or 13, they're both at Calc Chat, 11's at Calc View. Do either 15 or 17, they're both at Calc Chat, and then any of the odds 19 to 23, they're all at Calc Chat, 19's at Calc View. Do any of the odds 25 to 29, they're all at Calc Chat. Any of the odds 31 to 35, all at Calc Chat, 31's at Calc View. Either 37 or 39, both at Calc Chat, 37's at Calc View. Any of the odds 41 to 45, they're all at Calc Chat, 43's at Calc View. And I'll stop there, and we'll pick up the rest of the rest. Good deal. Any questions? Welcome back. Okay. All right. Research paper coming in. Incoming. Okay.
I'll have mine Tuesday.
Yeah, I've heard that before.
In my class.
All right.
So when's the last day of class you said?
What? The last day of this class is 1 week from today.
Okay. Yeah. So
research paper has to be in by then or you start losing points.
I thought last day was May 10th.
That's the last day of the term. That includes
last
final.
day of class is when we get the last test.
Yeah, next Thursday you'll get 2 tests, the Chapter 6 test and then the comprehensive test.
Okay. Yeah, I'll have the research paper Tuesday.
All right, yeah. All right, you too, thanks. You start work this weekend?
Me?
Yeah.
Yeah, I do.
You do? You sure you got, huh? All right, well, enjoy.
Oh, yeah. I got to go to sleep at 7 o'clock.
Because you got to get up
When?
at 6
I got to wake up at 3.
and get there when?
I got to be there at 6. It's an hour away. I got to clock in at like 5:30 though.
Why?
Cause it's like a huge plant, so I gotta walk like all the way. The parking lot. Have y'all ever seen Alabama Adventures parking lot?
Yeah.
That's about like what the parking lot is. You don't get a good parking spot, so it's like a.
You don't get a good parking place.
I could swear there'd be like several buildings, and every building would have a parking lot.
Oh no, it's 2 giant parking lots.
You need the exercise.
Yeah. I guess.
Yeah. Enjoy.